We all heard that electric vehicles are the future, with a whopping 70% of the world's vehicles to set go electric by 2030. But wait, just a minute, look at these articles. As you can see, they are showcasing something different. According to a research report from the Norwegian University, it turns out that a single EV has already emitted a staggering 13,608 kgs of CO2, even before hitting the road. Shocking, right? And that's not all. This study suggests that a single EV's emissions have resulted in the premature deaths of 3,600 individuals due to the associated pollution. It seems that while every country considers EVs to be green energy sources, they may actually be triggering the greenhouse effect. So, what is the solution for it? Well, this is the Toyota's brand new engine to replace the EV industry. Toyota has introduced an innovative solution, a brand new engine that runs entirely on hydrogen gas. This engine emits water vapors instead of carbon dioxide into atmosphere. In fact, the byproduct of this engine is safe for consumption, making it an intriguing proposition. If we discuss its efficiency, this particular engine boasts twice the efficiency of an electric vehicle EV engine, and it even replaces the engine used in the Tesla's popular Model Y EV during its prototype stage. I understand if you find this hard to believe, so let's compare the numbers. Toyota's hydrogen engine allows for a travel distance of 650 kilometers on a single refill, and it only takes 5 minutes to refill the tank. In contrast, Tesla's Model Y offers a range of up to 500 kilometers, but that requires a full day of charging. Impressive, isn't it? However, while it may appear that Toyota's designed this engine with environmental considerations in mind, the truth is that they were compelled to develop it due to the US government's ban on their regular cars. During the period of 2005 to 2015, Toyota experienced immense success in selling its vehicles, earning the reputation as the largest seller of the vehicles. However, a significant issue emerged due to the negligence of their workers and the lack of updates to their tailpipe technology. For a decade, Toyota continued to sell its vehicles without addressing the problem with its tailpipes. Eventually, the United States Environmental Protection Agency (EPA) became aware of this issue and demanded a thorough investigation report from Toyota. Unfortunately, Toyota failed to provide the required information. Consequently, the United States government took action against Toyota, charging them with violating the Clean Air Act. Additionally, they issued an ultimatum demanding that the Toyota pay a hefty fine of $180 million for their manipulation of carbon emissions. Toyota found itself in a predicament where they faced the choice of paying a fine to avoid a ban on their cars or suffering significant financial losses. Despite the challenging circumstances, Toyota sales declined further in the following 2 years, worsened by the impact of the COVID-19 pandemic. However, the automotive industry as a whole started to prioritize environmental concerns during this time. Interestingly, Toyota remained focused on conventional combustion engine and seemed hesitant to pursue new innovations. This approach raised concerns, especially when their sales only reached 20% of their previous levels, serving as a warning sign. Eventually, Toyota recognized the need to shift their focus and explore hydrogen engines, combining innovation and durability. They formed a strategic collaboration with Yamaha and initiated a Beyond Zero campaign, which aimed to achieve zero carbon emissions. The campaign involved the development of a hydrogen combustion engine. However, it's worth noticing that the idea of utilizing hydrogen as a fuel source in engines was not originally conceived by Toyota. If we dwell into the historical origins of this concept, in the 18th century, a Swiss army engineer named Francois Isaac de Rivaz had a moment of inspiration while firing a cannon. He wondered if it would be possible to power an engine's piston with explosive material instead of steam. As a result, he quickly devised a visible permissive engine that utilized hydrogen gas stored in a small balloon for ignition. However, this engine had a significant drawback. It had to be manually started every time and could only travel a distance of 6 meters. Due to its impractical nature, Francois ultimately abandoned the idea. Now, fast forward to 1860, a Belgian engineer, Athénée Lenoir, made a slight improvement to the same engine and created the first hydrogen-powered car through electrolysis, known as the Hippomobile. However, since electrolysis requires electricity, which at the time predominantly came from the internal fossil fuels, the focus of the automotive industry shifted towards the fossil fuel power engines. This led to the invention of the two types of engines, the diesel engine and the petrol-gasoline engine. Hence, the utilization of the hydrogen as a viable fuel option remained purely theoretical until 1966. It was during this year that the General Motors company conceived the idea of employing rocket fuel technology in regular automobiles. Drawing inspiration from the cryogenic hydrogen tank used in the Apollo missions, they developed the first ever hydrogen fuel cell car known as the electrifying. Unfortunately, this pioneering vehicle was fraught with a significant drawback. It essentially resembled with the potential of a hydrogen bomb, and as it contained cylinders of hydrogen and oxygen gases. As commonly understood, the combination of hydrogen and oxygen is highly combustible due to its both gases being highly flammable. However, let's consider that they managed to find a solution for these challenges. Nevertheless, operating the vehicles required a level of expertise akin to that of a rocket scientist. Just take a look at the dashboard. It resembles a control panel for a rocket. Furthermore, when examining its design, it became evident that the engine alone occupies more than half of the car's space. Consequently, despite its compact appearance, the car could only accommodate 2 people, rendering it impractical. Consequently, the van never made it to the commercial market. Before General Motors could address these issues and find solutions, a huge accident happened which stopped its production. During the Electrovan's testing, its hydrogen tank exploded and propelling the car's tail section half a kilometer away. Witnessing this incident, the world gained a clear understanding of the inherent dangers associated with this technology. However, let's remember that this is a matter of history. Nowadays, technology has advanced significantly and we can expect something better. So is Toyota thinking along the same lines? What has prompted Toyota to reintroduce this potentially dangerous technology to the market? What measures has Toyota implemented to ensure these vehicles and engines are resistant to explosions? To address the issues with their van, Toyota systematically tackled each problem one by one, starting first with the safety. The first problem they addressed was the hydrogen leak from its tanks. The original tanks made of aluminium and stainless steel had a low tensile strength, leading to leaks. Toyota sought a solution by option of carbon fiber, a lightweight material with a high tensile strength. These new carbon fiber tanks could withstand a pressure of 10,000 psi, a significant improvement from previous of 3,000 psi. With these enhanced tanks, Toyota introduced the Toyota Mirai, the first commercially available hydrogen fuel car in 2014. However, despite its popularity, the Mirai faced challenges in the terms of fuel cell efficiency. Unlike electric vehicles, EVs, that have a high efficiency rates ranging from 79% to 90%, the Mirai achieved only 25% to 30% efficiency. This was primarily due to the dual energy conversion process involved in the fuel cell electrolysis, where electrical energy is converted into chemical energy, which is called electrolysis, and then back into the electrical energy, which is called reverse electrolysis in the car's engine. The electrolysis process led to the damage and corrosion of the anode and cathode materials used, reducing the cell's lifespan. To overcome these limitations, the Toyota took a different approach. They decided to go back to the basics, using a hydrogen gas to power a conventional combustion engine, a strategy that proved to be masterstroke. Now, unlike the typical fuel cell process in EVs, Toyota compressed air and hydrogen in a regular engine, following the standard combustion process. This approach yielded impressive results, with the H2 engine achieving an efficiency of 40% to 50%, double that of the traditional engines. One of the advantages of the H2 engine is ability to generate more energy than conventional fuels, as it allows to complete the combustion without leaving residue. For example, while 5 liters of the diesel produced 45 megajoules of energy, the same volume of the hydrogen H2 generates 120 megajoules. However, a significant challenge still remains in the transportation of hydrogen. The infamous 1937 Heidemann disaster serves as an example of the dangers associated with hydrogen transportation, with the hydrogen-filled airships exploding catastrophically. Now, to address this, scientists are exploring new methods of producing hydrogen fuels at the hydrogen stations using the solar energy, aiming for a more cost-effective and efficient process than the initial solar panel approach. Recently, the University of Japan has made a significant breakthrough in the field of photoelectric cells, as reported by IEEE Spectrum. The cells have the capability to produce hydrogen through the process called photoelectrolysis. Normally, water electrolysis requires electricity and specific electrodes, anode and cathode, to generate hydrogen and oxygen respectively. However, In this case, photoelectrochemical cells, the electrodes absorb different wavelengths of sunlight to separate hydrogen and oxygen. The photoelectrochemical cells operates by utilizing a doped anode and cathode. The anode is doped with the titanium dioxide, serving as an N-type photocatalyst, while the cathode is doped with a silicon carbide, acting as a P-type photocatalytic. When sunlight including UV rays reaches the cell, the titanium dioxide absorbs the UV rays and its electrons becomes excited. These excited electrons flow from the anode to the cathode, generating an electric current and producing electricity. This same method can also be employed to produce hydrogen H2 at hydrogen stations. The efficiency of this engine is remarkable to the extent that it has the potential to replace conventional electric vehicles (EVs). Despite having such a revolutionary technology, Toyota is not only focusing on improving its conventional engines, but they are also making significant advancements in hydrogen engine technology. Remarkably, they have been successful in these endeavors as well. So guys, if you like the video, give a thumbs up and subscribe to our channel. See you in the next video.